Hi everybody, in this video I'm going to introduce a new type of statistical test. It's sort of an extension of the mean comparison ideas that we've covered in the t-test sections if you've been following these videos in sequence. If not, we're still going to cover why we need to do ANOVAs, why we can't just do a series of t-tests, for example, and what an ANOVA is as a basic concept. In the future, of course, I'll walk you through some actual example problems, we'll see the equation, and we'll talk about assumptions, all of that kind of stuff. But I'm just going to introduce the basic concept here. So once again, as sort of a backdrop for this, a t-test compares the means of two different groups usually. Now it doesn't have to be two different groups, sometimes it's the same group at two different times as we've talked about, and sometimes there's only one sample that you're actually comparing to a criterion. But in any case, we're working with basically two measures, right? We're working with two means or one mean and some kind of set criterion. Now, there might be lots of circumstances where you actually want to compare more than two groups simultaneously. For example, let's imagine that I've got some kind of new treatment, some kind of new, we'll say it's a new drug or something that treats, we'll say, depression or something, right? It would make a lot of sense that I have a control group now because I want to compare whether my drug actually works compared to no intervention whatsoever. But then maybe I'm not sure how much dosage I should be giving to people. In fact, maybe it turns out that lots of treatment, a higher dosage, is more effective than some treatment, but some treatment is also still effective compared to no treatment. So that would be really important to know, and it'd be nice and convenient if I could figure this all out in one particular study. So this way I don't have to run two mean comparisons and then do a new study with two new mean comparisons and so on. I could do all of this simultaneously. Now, the problem, of course, is that a t-equation allows us to compare only two group means simultaneously. And so that's kind of a problem. Let's talk about why that's a problem. Now, one thing I could do if I have these three groups is I could compare each group mean to each other group mean. In this case, if I have three means, that means I'm going to have to do three mean comparisons. So for example, first I could compare the mean of group 1 to the mean of group 2, for example, the no treatment group to the little treatment group. Then I would have to compare the mean of the no treatment group to the lots of treatment group. Then I would have to do the little treatment group to the lots of treatment group. And in this way, now I've compared all three means, but I've run three different t-tests. See, that is essentially the problem. You'll recall that for every statistical test we run, particularly the t-test, as we've covered most recently, allows a 5% probability of making a mistake even by rejecting the null hypothesis. In other words, once you say, I think there's a difference between these two means, the statistical significance idea says you're going to allow a 5% chance of error there. 5% or lower, and of course it's hopefully lower, but usually we allow up to a 5% chance of error. So the problem here is if I'm doing that 3 times, I'm now multiplying my error rate. Let's talk about that a little bit more. So again, if every test I allow gives 5% chance of committing a type 1 error, then what I'm essentially saying is that if I multiply that 5% chance of error times 3, what I get is, of course, an overall error chance of 15%. Okay, so in other words, if I've run 3 different t-tests and maybe I found differences all 3 times, and I found a p-level of 0.05, in other words, statistical significance, if all 3 were statistically significant, what I'm basically saying there is overall I've allowed a 15% chance of a type 1 error. Now that's too high based on our conventions. Again, 15% is not what we usually allow. We usually allow only a 5% chance. So that's a big problem. Now, let me give you maybe an analogy that'll hopefully make it a little more understandable. That's a little bit like saying, hey, there's this nice big lake here and there are alligators in it. You have a 5% chance of getting eaten by an alligator when you swim across the lake. Now that's pretty low, right? You have a 95% chance of getting across the lake just fine. But would you then rather swim across the lake only 1 time, or would you rather swim across it 3 times? Right? If you swim across it 3 times, now overall you have a 15% chance of getting eaten by an alligator. That seems like too much, right? That's essentially the problem here with the type 1 error risk rate. If we multiply it by 3 times, we have a much higher rate of making a mistake overall. So we don't like to do that. So you might say to yourself, well, Dr. Ricks, why don't instead we just kind of adjust our error rate for each individual t-test and we'll decrease it? Could we do that? Well, that might make sense. For example, you could take the three t-tests, and because we want an overall error rate of 5%, you divide that 5% overall error rate by the three tests. That's what this looks like. You've got a 5% chance of error rate divided by 3, and that leaves us a 1.7% error rate for each individual test. So in other words, that would be like saying I'm going to run these three t-tests, and every t-test I will not reject the null hypothesis unless I have only a 1.7% chance of committing the type 1 error. Now again, that might seem like a good idea. That's a little bit like removing some of the alligators out of the lake before you swim across. Now the problem, of course, is that therefore increases our likelihood of there being a relationship, but us saying we don't see the relationship. That is the definition of a type 2 error, or a false negative. Okay? And that's a little bit like saying, hey, I swam across the lake 3 times and I didn't get eaten by an alligator. Therefore, it's perfectly safe there are no alligators. When in reality, of course, there still are alligators. So I hope that analogy kind of helps you to understand what's going on. So what do we do here? We're now stuck between a higher risk of a type 1 error and a higher risk of a type 2 error. Do we have to choose the lesser of two evils? Turns out no. Some very intelligent people came up with something called an ANOVA. It's a test that allows us to simultaneously compare the variances due to the mean differences, and then including or taking into account the variances that exist just within the people who were measured. So this is something called an ANOVA. It has an overall error rate of the 5% for the type 1 error risk, and it doesn't increase your type 2 error risk either. So this is very important. It's vital for what we'd like to do here in these particular scenarios. So it's overall called an analysis of variance. A little note here is that's a little bit of a confusing title because most of the statistical tests that we run are analyses of variance. A t-test is an analysis of variance. However, this name has stuck for this particular kind of test where we compare 2 or 3 or 4 means or more means to each other. So that's fine. We'll just continue to call it an ANOVA, which is short for analysis of variance. So as I said, when we have an ANOVA, the circumstance that is correct for an ANOVA is when we have 2 means, or 3 or 4 or 5 or 6 or 7 or on up, actually, it turns out. So I said 2 means because it actually is appropriate for a test with just 2 means. You could do a t-test, that's fine. You could also run an ANOVA because it uses the exact same principles, exact same information to arrive at its answer. Now, we'll see how it's different once we get to the equation in the future videos, but we're not going to worry about that right now. It's important to recall that just like our t-tests had different versions, there were independent samples t-tests, dependent samples t-tests, and one sample t-test, we have that same kind of thing for ANOVAs. In fact, some ANOVAs do assume that the groups making up the means are independent of each other. They have no influence on one another. And then others, by design, are dependent. In fact, you can have a repeated measures ANOVA. So I'll give you a couple of examples there. So this is an independent samples kind of look. It was like we talked about, as let's say we have a control group that receives no treatment, then we give a small dose of the treatment to another group and a large dosage of the treatment to the third group. And in this case, I'm measuring, we'll say, their depression symptoms after this treatment, and I want to compare them to one another. So every single mean gets compared to every other mean, and I have 3 comparisons in this particular case. Now, a dependent samples design could be like a repeated measures. In other words, I measure everybody who I've recruited to my study before I give them any kind of dosage. I measure their depression levels before. Then I give them a single dose of the treatment. I measure their depression levels after that. We'll say a month after that, for example. Then I give them a second dose and I measure them one more time, maybe a month after the second dose. Now, all of this might be important depending on what it is you're looking at. Especially in this case, what I might like to see is that I want to see an improvement in the symptoms from time 1 to time 2, for example, so that I can have evidence that dose 1 is effective. But it might turn out that maybe dose 1 is just as effective as dose 2. I wouldn't know that with just a t-test. But with an ANOVA, now I can assess that. However, it also could be I see marked improvement after the second dose, even from dose 1. So all of this would be important information, especially if I want to know how best to administer this drug to people who have depression symptoms. And now I can have that kind of information. So as a quick recap of what we talked about today, an analysis of variance, or ANOVA, is a test that allows us to compare simultaneously the means of 2 or more groups. So whereas a t-test allowed only 2 means at one time, an ANOVA allows us 2 or more groups. And so we can test 3, 4, 7 means together at once. We like an ANOVA because it doesn't artificially increase our risk of a type 1 or type 2 error. And so therefore it's very useful and efficient for our tests and our ability to figure out how the world is working. Now, this is all we've covered so far. In the future, we're going to start talking about the hypotheses, the assumptions of these kinds of tests, and we'll actually start working through problems, and we'll see what the equation looks like. So we will practice all of that in the future, and I will see you then. Thanks for bearing with me.